Welcome back. So let's move ahead and see what more we have in the field technique. Okay. So as we have seen in the previous lecture, we were talking about the detailed mapping of the surfaces. So let's see what more is left out in this field technique part. So the most essential which comes with the base maps and all that is your topographic mapping in the field. So detailed geomorphic mapping includes preparation of the base maps and profiles, and mainly we are talking about the topographic profiles of the landforms. That means your deformed landforms. Many landforms produced by paleo earthquakes are as small as 1 to 5 meter in height. So in some cases the question which comes in our mind that how we will be able to map the features using or identify the features with height less than 1 meter, where we are using the satellite data with resolution of 2.5 to 3 meters, and this always remains a question. So what experience we had while doing this such type of surveys, that we of course we have demarcated the fault traces using high resolution satellite photographs, but and then moving to the field area at that particular site, we also consider if we come across any feature or the landform with the deformation could be less than 1 meter, and that probably is the indicator of the paleo earthquake. So we should not miss out even the features which are present in that region which has the height less than even 1 meter. So what we do is we generate a very detailed map using GPS or using the total station, and generate the contour maps with an interval of 3 to 15 meter or even less than this you can do, and very high resolution topographic map you can generate with the contouring, and which is ideal to understand the overall geomorphic expression. The example which has been given here, where you won't be able to identify the deformation very clearly on the satellite data, but in field the detailed mapping helped in identifying the deformation which has been shown here, and then contour interval was even less than what has been shown here, even that what it shows is around 20 centimeter of the contour interval. So this portion helped in identifying the offset of streams here, and that was taken into consideration that this is probably the fault line, and across this the trenches were been open, and this is from the northern Anatolian Turkey, northern Anatolian fault, where the trenches were open in 1990 and 2002. So you can have such maps with an high resolution contours which can help you in demarcating the landforms which you will be unable to mark using high resolution satellite photos. So topographic mapping in the field is extremely important, and there is another map which shows from US with a contour interval of 20 centimeter, which helped in identifying the displacement of the terraces. Now fault scarp profiling, Paleolithic, I am just using this word because we have the ancient culture which usually the archaeologists take into consideration, the Paleolithic, Chalcolithic and all that. So Paleolithic style, the ancient, not very ancient, but of course it is an old style of mapping the landforms. We used to use theodolite, or maybe we used to use and calibrated post here, and then with the intersection of the eye here with this person leveling here, then he will say okay fine, whether the point is intersecting here with this, then he will say yes, then this point will be marked as the height of this point here. Okay, so this will give the height of this particular point. So this is what we have, the Paleolithic style we used to do. and then we came up with the total station mapping using high resolution like what we are having digital data. So when we see or identify the fault scarp using high resolution satellite data, and as well as we have demarcated or located this feature in field, it is most ideal to take the profile across this one. Okay. And this black dotted line is showing the probable trace of the fault, because this portion is already showing you the retreated or erosional scarp. The scarp got eroded, then the faults on the surface somewhere lies here. Okay. So it is ideal to take the profile which crosses the undeformed area and the deformed area. So you have to decide and finalize your transect accordingly, so that you cover the undeformed flat area as well as the deformed portion. So multiple points you can take crossing the scarp or the landform. So they are just the points which you can decide and you can take, and that can help you in generating the topographic profile. So if you have this profile which has been shown here, and if you draw a line here and parallel to that here in this the undeformed surface and the deformed portion of the hanging wall or the foot wall, then that will give you the height of the scarp. Further, now we have started using the total station, which gives the millimeter accuracy points, and this will give you this points. What we will get will be having x, y and z. So you will have the coordinates of each point which will be given here, and with the help of the best fit line which has been drawn here, you can talk about the height of the scarp here. Then another way to identify the deformed landform is to generate the shaded relief map draped on the satellite topographic mission data, or the DM which has been generated using any high resolution data with an stereo pair capability. So this you can easily make out in a very flat surface. This slightly raised landform here, which are indicative of the fault traces. So ground truthing, when we did here, you can see this part in the ground. So this is slightly elevated hill, and then you have the flat surface. So this is from Himalaya. So this portion here is your Indo-Gangetic plain, and this is your sub-Himalayas. And this contact is your contact which we call Himalayan frontal thrust, or the plate boundary between the Indo-Gangetic plain and the overriding Eurasian plate. So ground photograph of this you can look at with this one. Okay. So you have the hilltop which has been seen here is this hill, and then the elevated portion which you see over here. So if you draw the profile here, then you have something like which goes here. There is an elevation here which increases at this point, and this is the same here what you see from the ground. So this is your elevation which has been marked here. Okay. So exactly the same area. So we can pick up this deformation using different ways or the techniques which are available, and it can be easily used. Either you are using high resolution satellite photos, or you are using aerial survey data, or you are using the digital elevation model and draping the images on the digital elevation model. So again, the next step will be that you identify the fault scarps and you select the trend site. Okay. So we selected the trend site over here in this portion. So what we did further was that this is another fault which I was showing in the previous image. This is the same image which we have, and ground photograph if you see is this one here. Okay. So the previous one was from here, and this one is another fault which you see the portion which is up and this is down. So that same you can see the up and down here. Okay. So earlier we used to do the topographic mapping using auto level, okay. But now we have with the more development in science and technology, we have high resolution total stations with which we can generate millimeter accuracy maps. So we use either real-time kinematic. This is what has been shown here. This is a total station we have, and then with the help of the line of sight, you will be carrying one prism which is mounted on the post, and this post or the rod is calibrated. So you have the height of this. So this part we'll talk when we are talking the detail about the total station and all that. So with the line of sight, you can easily map the area, putting your the pole at different location of your interest, as it has been shown here. So you have the total station here, and this person will keep moving and try to map the topography, or try to map the landforms here. This again with the total station, and this is what we have. We call either the real-time kinematic survey or post-processing kinematic survey using the total station and GPS. And further, I'll discuss this in very quickly in coming slides, that we also use ground penetrating radar to identify the subsurface deformation. So what we do in short, if you take, so we are doing the first using the satellite data, then we are using the mapping of landforms in field, either using total stations, and then third we do. So this is all related to the surface mapping, and subsurface we do GPR before we get into the trenching part. Okay. These are the simple steps which we follow without any constraints or boundaries. We must do this. So this is an example of the same what I was talking about, that we identified the fault trace using the high resolution satellite data, went into the field, identified the landform at that same location. We use total station and we prepare the topographic profile here. So now you can see that this topographic profile is hardly the height is 1.2 meter, and as I was saying that whether we will be able to pick up the deformation of 1 meter or less than that, to some extent yes. If the feature is very sharp, you will be able to pick up this deformation even on the satellite photos. And nowadays, with the advantage that that you have the digital satellite data, okay. So you have the data on your PC, you can enlarge this area of your interest, and then you can view this in 3 dimension. That will increase at least the resolution, which will help you in identifying even the minor features which are having height less than 1 or maybe around 1 meter also. So this what we can what we are showing is that this is with the experience, and what actually we did, that this with the help of this is Cartosat data, we were able to pick up this fault trace, and this is the location where we see the topographic variation, and then we mark the fault scarp. Then after this we go for trenching, but this is another one more example where we wanted to map the displacement along the scarp or along the surface, or sorry, displacement of the surface along the fault, and the offset of the stream along the fault. Okay. And this what we did, we took a number of points with the help of total station, and with the simple triangulation we have generated this offset of stream. So this streams flows somewhere here like this, and then we have the scarp here, and then it goes like that. Okay. So, this offset of ridge as well as the small stream which we were able to pick up on the satellite data as well as in the field. So, we were able to precisely say this. Okay. You could do this putting the tapes and all that, the measuring tape, and you extend and keep measuring at what is the offset, but there are restrictions. For example, there is an house setting here, and you may not be able to cross very straightly because you are having trees in between. So, the best way is to do a detailed mapping, and that what we generated was the digital elevation model. So, this portion is the higher ground as compared to this one, which is light yellow, and the orange one is the higher ground here, which was also seen in the previous photograph over here. Okay. So, this portion is this one here, and the scarps run like this, and this is the offset of the terrace riser. Okay. And then this helped us in deciding the location for trenches. Okay. So, I will get into this business of trenches later on, but this is again another example where we use the data and generated high resolution contour maps. So, coming to the area of bias, what we did was, this is at this location here, we took the detailed mapping was carried out using total station, but we fixed up the site after doing a detailed GPR survey in this region. Okay. So, using geophysical methods is another advantage before getting into the trenching part. Okay. So, as I have been telling that we use satellite data, then go into the field, do the mapping, and then coming down with the before we get into the trenching part, we do the geophysical methods. So, there are different geophysical methods which you can use. Either you can use seismic reflection, you can even use resistivity survey, you can do GPR, but what we have the good experience with the GPR, ground penetrating radar, which can give us a very excellent high resolution subsurface profile of the deformation or deformed layers up to 8 meters, or even if you can go up more than 10 meters. But for us, for putting trenches, 6 meter to 10 meter is quite good enough. Okay. So, geophysical methods have been used in terrestrial paleoseismology in 3 ways. One is as a reconnaissance technique to define shallow stratigraphy and structure in a fault zone or liquefaction area in order to locate the optimum site for further trenching or drilling. So, the optimum site for trenching is extremely important, because this is going to be a very tedious job, because if you miss out the fault, you may keep digging the area, and which may not be allowed because of the environmental constraints. So, you have to be very precise that when you would like to put the trench to do a detailed paleoseismic studies. Okay. So, the next one is that we usually do the geophysical survey to reach greater depth, because with the help of trenching you may not be able to reach greater depth. So, by trenching maximum up to 5 to 6 meter, you can go, and drilling up to 15 to 20 meters, and so, but with the help of geophysical technique you can go further deeper to identify the fault trace. Okay. And finally, the third one is for detecting the buried faults that have no surface expression. So, these are 3 important steps why we usually do geophysical survey before we get into the trenching part and do the paleoseismic investigation. So, in our case, what we have done in India, mostly we have used GPR to identify the deformation, which goes maximum up to 10 meters and so on. But now we are trying with the other methods that if we can go up to more than 100 meters or so. Why to use geophysical method? So, there is another question here. So, the answer is to locate appropriate site for trenching as a substitute for trenching, but will not be able to date the events. Okay. So, you can identify the deformation at the depth, but unless and until you are not dating the deposits or the sediments, you will not be able to classify or characterize the fault as an active, and you will not be able to date the events, the paleo earthquakes which have occurred on that particular fault. And third, we do to understand the geometry of the fault trace at depths. Okay. That is in crustal scale cross section if you want to do, which goes more than 1000 meters or so, then you will be able to at least say that this method is important to at least understand the geometry at the greater depth. Then in recent years, a few investigations have used multiple techniques. Okay. And those techniques are gravity, vertical electrical soundings, 2D resistivity, seismic reflection, seismic refraction, electrical resistivity tomography ERT, and P wave seismic tomography. So, these are few more investigations or the techniques which are been used to for the first step, as a first step for your paleoseismic investigation. So, in case of seismic reflection and refraction methods, they can contribute in two ways to the paleoseismology. One is towards detection of fault, and second is in characterizing the faults. Either the stratas are folded or they are tilted by faulting. However, the simple detection of a fault plane may not in itself provide any data on timing and magnitude of an individual fault or paleo earthquake. Okay. So, for us this is important that we need to know that when the earthquake, the last earthquake occurred, and when there were more paleo earthquakes in the past, and what was the magnitude of that particular earthquake, individual earthquake, or what was the magnitude of the previous paleo earthquakes. So, in short, what we conclude is from this that we can use geophysical technique, but just to locate the deformation and just to understand the geometry of the fault at greater depth, but we won't be able to use this information in categorizing the fault whether it is active or not, but at least to some extent we can categorize the fault in the pattern of deformation, whether it is a vertical fault or it is just a pure strike slip or a normal fault. That at least you will be able to categorize, because you will get in profile with of greater depth, but otherwise the identifying the paleo earthquakes, it will not be possible, because you are unable to look at the sediment succession, you are unable to date those sediments. So, you won't be able to classify or characterize the earthquakes in that region using that. There is an example photographs which has been seen for the seismic reflection tomography, where you have the tomography line extending from down thrown block in the foreground and the up face scarp in the middle here, which goes right up to the top. So, this is the scarp here, this portion is up, this is down, and this is what has been done for the seismic reflection. This is the profile which was been obtained using seismic reflection going up to the depth of 50 meters. Then you can also do the high resolution seismic reflection when compared with the trench log. Okay. So, this has the trench is hardly 2 meters, but with the seismic reflection you are able to reach right up to 14 meters or so. So, ground penetrating radar generates high resolution near surface image that resembles seismic reflection results. Okay. The similarity arises from the common use of transmitted waves that are reflected and then detected by the receiver on the surface. This is very much similar to the seismic reflection data. So, in contrast, the compressional elastic wave utilized in the seismic reflection with a frequency of around maybe 100 hertz, radar uses transmitted electromagnetic radiation with frequency ranging from 80 to 300 megahertz. So, this you can have more also, and even you can have less megahertz frequency antenna, but you can this frequency antennas will give you a very high resolution image, georadar image. So, the material with high electric conductivity such as clay in some regions, okay, if you come across, or the fluids with high dissolved solids will rapidly decrease the depth of penetration of the georadar, and this is very much similar to what you will experience in case of the resistivity survey. So, there are limitations, but you can increase the gain and try to increase the penetration depth of the GPR waves. Okay. So, this is an example of the ground penetrating radar profile which has been shown here. They have been able to go up to 15 meters. So, much better than what was been done in seismic reflection, and further it was been compared with the trench which was been dug in this region. So, this is the logged area which has been seen here, and which shows that clear cut displacement here. Then you have the electrical resistivity tomography, which with the help of which you can go up to the depth of more than 100 meters, which has been shown here, and with the change in the density or the of the material, you can easily make out the variation in the lithology, and which has been compared here with the trench which was open in Bulgaria. Okay. So, with this I'll stop here, and we'll continue in the next lecture and see what is more left out in this part, and then we'll straight away move to the respective tectonic environment and how we have conducted the paleoseismic studies in those regions. Thank you so much.